Right. So let me share the screen. Share the screen for you. All right, now you should be able to see it. So this is the homework. I don't read the stuff on the top, okay? Because this is from the last year or even year before the last year. But we will update it a little bit, but the flavor will be the same. And we will update some details, but it won't change much. Anyway, they will be originally there are 4 problems, okay? So the first problem is from Marsha's lecture, okay, from what Marsha gave you during the very first time when we met, okay. So all you have to do is basically rewatch the lecture, or maybe you just remember the stuff. I never do remember the stuff, but you can rewatch it and solve this problem, okay. So it's not super complicated, okay. This is just based on your knowledge. All right, the next one is a bit maybe complicated for you, but I do want you to go over it, okay? So that because you at least remember something of this mathematical physics stuff that we and vector differential operators that we look like rotor divergence and stuff, okay? So that you feel yourself a little bit more grounded to some fundamental stuff, okay? So there you have to, this is basically a two-dimensional world where you have this particle that is located at 0 at the origin, okay? And then this is the expression for the electric field from this particle, okay? So it's a radial field, right, which decays as a square of the distance, okay, because it's a cube here, but the first order is here, right? So, and then all you need to do is to compute the divergence of this. So you have to just expand this as Rx, Ry, right, and this one, and then take the derivative. You can use any analytical software for this. You can use mathematics, or you can use a symbolic toolbox in MATLAB to take the derivative, but you have to tell it what kind of derivatives you are taking. Okay, all right. So, and the same thing you can do, you can also do to compute the rotor. You have to get the definition of the rotor and try to appreciate the value of the rotor in the two-dimensional space from a charge, from a radial charge, okay? From a single charge, right? With radially oriented field lines, okay? Then there was a question about what will happen if you have 2 charges at location R0 and location R2. Okay, so you will have to repeat the divergence and rotor for the second case, and then you have to generalize. Okay, so just write down the expression. So you can ask questions about this problem, well, about any problem, but about this as well, to me and Dasha, and we will help you. Okay, so problem 3. Problem 3 is about Maxwell equations and about the quasi-static approximation. I skipped it during the lecture, but the material is in the Ilmaniemi and Sarva's book, and it's also in a paper that I shared with you on the basics of MEG. Okay, I will point you which formulas you need to try to understand, and then you will need to answer this question. This question is actually very interesting because as you said, as you know, as I said, and you now know, we are using quasi-static approximation, right? So that a dipole or something, a source in the brain, when it changes its activity, we immediately see this change on the sensors, on all sensors at the same time. Okay. And this is very different when, as if you compare the situation we have in acoustics, right? When you have a source and you have a set of antenna array, right, microphones, and then you have the source arriving at microphones, and of course it will be arriving at delayed times, okay? Just because one microphone is further than the other, right? Here we don't have this luxury, and if we had such a luxury, the inverse problem would be less ill-posed. Okay, so therefore the question here is to imagine the fantastic world where the ratio of the frequency of your activity to the conductivity of the brain tissues. Okay, what ratio will result into phase shift of pi over 4, okay, between the between the magnetic between the at some fixed distance. Okay, the distance is encoded here. Okay, so between between the magnetic field and the components of the electric field. Okay, so then, because if this happened, we would really have much more information about where the source is, because it would not only manifest itself in, let's say, this positive and negative topographies, right? But also on the top of topographies, we would have arrival times. Okay, and if we could measure them, we could definitely infer more information about the source. But it's not the case. But you can always try. Okay, and you can try and see what unrealistic conductivity or unrealistically high frequency of oscillations would be required. Okay. Also note that I'm talking about pi over 4, about phase, not about the absolute time, but about the phase. So if the frequency is high, then the period duration is small, right? But the phase will be measured with respect to this period duration, right? So that, and I can tell you that frequencies have to be quite high, unrealistically high if you keep the same sigma, or you need to somehow increase sigma. I don't know how. Okay. Uh, or I mean decrease sigma, yeah. So anyway, now the fourth problem, you have to imagine yourself like a designer of an MEG system, okay, or magnetoencephalographic system, and you have to master the script that computes the forward model. Okay, you can do this either using the MATLAB script that will send it to you. It starts from very basic principles and goes over formula that we looked during the lectures. Okay, you can also always use again Almaniemi and Sarva's book as a helper here. And you can go, and all you need to do is this: you need to consider a spherical head, okay, like Jack in the Box has, uh, and you'll consider source inside this head, and I will ask you to simulate the magnetic field that is measured by a single coil. Basically, very simply, you don't have to integrate over the entire coil. All you need to do is just to compute the magnetic field at the center of this coil. Okay, just use these formulas to understand how to use them. Okay, then in the second case, I will ask you to calculate the thing which would be measured by the gradientometer or gradiometer configuration. So this is where one coil is bound in one direction and the other coil is bound in the opposite direction, and apparently the currents will be directed in the opposite sides, right? And then they will sum up or will subtract one from another, and then you in fact will be measuring the difference between the field in this coil, measured in the center of this coil, like some approximation, and the field measured by this coil. Okay, so, and this will be this is the radial gradiometer, because you are like the first coil is closer to the head and the other coil along the radius is displaced from the head surface, right? And this is the example of tangential gradiometer, where you all have the same thing. You have two coils, but I mean, don't pay attention that they're drawn differently. It's not your level of like details. Okay, all you need to do is to compute the field in the center of this coil and in the center of this coil, and subtract the two in order to see what will you measure due to a dipole located inside the sphere. And there are some additional like exercises. Okay, uh so the homework is graded. The homework you will need to turn in within, say, 2 weeks from Friday. Dasha will distribute it on Friday. Okay, what I suggest is that you read the homework, try to understand it, and if you have questions, you prepare them for the lecture with me or for the seminar with Dasha. Okay, I think the next Tuesday won't happen, right? So that it will be Friday's lecture, right? So yeah. So yeah, you prepare your questions for Friday's lecture, and then you have time to complete the homework. Okay. Please don't postpone your questions till the moment. Don't postpone approaching the homework till the day of the deadline. Okay. Because you will have questions. Okay, but you won't have an opportunity to ask them. Well, I mean, you will, but it will be very little time for me to answer and for you to implement my answers, right?
Sorry, I have a question.
Go ahead.
I didn't get. Should we look through and prepare our questions for this Friday? You mean we have lectures
No,
with
no, no,
you
no,
this
no, no,
Friday night?
no, no, no. You will have seminar on Friday with Dasha, okay?
Mm-hmm. Mm-hmm.
We can tentatively, I think, if you don't consider it official, or maybe yes, because Dasha can do almost everything, we can modify this homework and give it out to you. Let's say send it out to you on Wednesday, okay?
Ah,
So that yeah, let's do it this way because then it will give you more time, okay? So we
uh-huh.
will do it on Wednesday, and then you'll have Wednesday and Thursday to look at it and generate
Mm-hmm.
questions. So you can look all together. I mean, okay, see, listen, I I definitely I can't prevent you from like consulting with each other, right? Just no way. And you can consult with each other, no problem. You can generate common questions, but you should complete the homework on your own, okay? Because if there are identical homeworks, they will be graded with zero. Okay, please don't no offense,
Mm-hmm.
nothing, but just some academic proper academic behavior. Okay,
Okay, that's
so
natural. Okay.
and especially given that you will have mistakes in the homeworks, and because there are infinite number of mistakes and only one proper solution, if you have two identical mistakes, and your letters, your symbols are labeled with the same letters, well, there is a great chance that you were cheating. Okay, so uh, anyway, I again, I assume that you're conscious enough and that you took this class not to cheat, but just to learn something. Okay, and I also realize that it may be a tough class for you to take. So we are very loyal, but as long as you are like honest with us. Okay, so all right. So yeah, so we will try to give you the homework on Wednesday night. And then you will have, or maybe midday Wednesday, because we just need to change some formal stuff here. And then you will have 1.5 day before the Friday, so you can take a look at it and ask Dasha questions. Then you can try and do it, and then we will have a lecture next Friday, right? Not this coming Friday, but next Friday, and you'll be able to ask me questions, and then you will have till another Friday to complete it. Okay, so we will give you on Wednesday, but the deadline is not next Friday, but and not the next Friday, right? But let it be let it be the Friday more than 2 weeks from now. Okay, two weeks
Ah,
and 2 weeks and 2 days from now. Okay.
uh-huh. But
Yeah.
you mean Wednesday is tomorrow. You are giving
Yes. Yes.
okay.
You see my screen, right?
Uh-huh.
So tomorrow we'll give you the homework. Okay, here.
Mm-hmm.
You will have Thursday and the rest of the day of Wednesday and the
Mm-hmm.
first half of Thursday to look at it. And then you will have Dasha on the third
Yes, answering our
ask her
questions.
questions. Then
Uh-huh.
you can start doing it, okay, until the
Mm-hmm.
10th, okay? On the 10th, we will have a lecture. You will have time
Mm.
to ask questions, okay, about this. So you always have this document where you can write your question.
Mm-hmm. And after
And
that, we
then
have one
yeah,
more week.
and after that you have one more week. Yes. So the
Okay.
deadline is if I didn't goof, so the deadline is
17th.
on the 17th. Yes.
Okay.
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 So we are very loyal. Again, I'm saying it's because it's not about to like punishing you or something, you know, but to somehow enrich you with a piece of knowledge. Okay. So yeah, that's about the homework. All right. So now let me use this beautiful piece of equipment called Samsung Galaxy Tab. And let me try and share. So I need to allow for sharing. No, not this. Multiple participants. All right, now I have to share screen, notch it. All right. So, okay. Uh, so let's start a new lecture here. Um, okay. And then let's choose a, no, this is not what I wanted. Okay. This is horrible. Anyway, here's the. All right. So, and I remember it was this time when I somehow figured out how. No, no, that was not it. Okay. All right. Uh, it's Yeah. Okay. So here are the so let's let me, since it was some time from the last lecture and from the last seminar, let me remind you a little bit what we have done, about the basic stuff, about um the the ion channels, right, and all these electricity basics and electromagnetic theory. You will have a chance to refresh your mind during the homework preparation. And after having in hand the theory, we started to work on something more practical. We started to look for basically for the methods how to explain the data, right? The data that we usually measure. If you draw several channels on the same plot, right? They look something like this, usually, typically. And then you this is time, right? Each time series is a channel time series, right? Channel time series. And then and this is dependent on what you are measuring. If you are measuring voltage, if you measure electricity, then it will be voltage. If you are measuring magnetic field with magnetometers, will be Tesla, right? And if you are measuring gradient, which is the difference between two uh, magnetic fields, uh, for a fixed distance in space, right? It will be Tesla by meter. Okay, so this is the scale. And your question, if you let's say if you select, for instance, certain specific latency corresponding to some time t0, then you can draw this multi-channel data. You can draw them on a topography plot. Okay, so where on topography you have sensor locations, right? Okay, and then at each sensor location you have basically these measurements, right? So one comes here, the other one, let's say, comes here, the third one comes here, and etc., right? And then you can interpolate, right? You can interpolate and draw something like this, like, for instance, this kind of picture. Something like this, right? And I will not choose blue one, but I will choose the green one, something like this. And there are maybe something else, but very low amplitude. But this is the most pronounced one, which ideally corresponds to a dipole. And if you are measuring EEG, then this dipole will be oriented approximately this way. And if you are measuring EEG, the dipole, now EEG, right? The EEG this way,
Yes.
EEG, yes, and MEG this way, right? Because this corresponds to a dipole that is located somewhere in the brain, producing magnetic fields, right? And let me I want something at this point, by agreement, by some we just agreed to do this. Where it's negative, it means that the field is leaving the head, and at this point the field is returning to the head. Okay, so it rotates this way, and so that's why your dipole is if you are measuring magnetic field, your dipole is oriented in this direction. Okay, so uh now the question was to find this dipole, to basically say that, okay, we have a brain, and it is inscribed in a three-dimensional coordinate system. Okay, and you have some candidate locations in the brain, many points on the cortex, which you can extract from the MRI data. And then you are interested in where on Earth, or actually not on Earth, where on the brain, a dipole is located. Okay, and this dipole has trying to find the black one here. Okay, the dipole is located at some point R, radius vector, right? You can project it, of course. You can see that it's over here. And you are interested in finding this location. Okay, so we started from a very simple setting. We said, okay, let's assume that the brain is that the dipoles oriented orthogonally to the cortical mantle, right? So if you consider a cortical mantle, like gyrus, another gyrus, whatever, So the dipoles will be oriented perpendicularly to the surface, right? And then we consider the situation that you have indeed only a single time slice here, okay? And then what I've shown to you that all you need to do is to basically, you have to sample your model, you go through your model, which is your forward model G, which depends on R, and theta is fixed, right? You always know the orientation of the dipole. I will put a star here that is fixed, right? And you want to find such G that of your data at T0, right? Again, a vector, that cosine between these two guys is maximized, right? And that was very simple. That was very intuitive, right? Because everything was basically like one dimensional, but you had a single time slice and you had a single dipole. Okay. Then we looked at the plots that we have. If you, let's say, if you scan through the entire brain, how will such a plot look? It doesn't look great because it's not like the region is not the region of high values of this cosine. They are not. This region is not like is not connected, right? It's kind of distributed over different locations, and if you threshold it, we find that actually there is, even with a very high threshold, we find there is quite a bit of locations far away from the true location of the dipole are highlighted. Okay, and then we also remembered about the real life scenario that we never know exactly the geometry of the cortex, right? And therefore, we decided to relax the orientation constraint, right? And remember, I told you about those triplets of dipoles, blah, 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 right? And then we said that, okay, in fact, instead of G R theta fixed, we have G capital or maybe G small, doesn't matter, matrix of R, what theta we had oriented along X direction. Sorry, it's a vector. It will be a vector this way. Yeah. Get rid of this. Okay, will be a matrix. Okay, but this will be of R, but of theta along X, G R of theta along Y, and technically G R theta along Z. Okay, right? So and then instead of a single vector, we had now three vectors, and we had to solve the problem of finding the R, given that we don't care about orientation anymore, finding the R for which our X of T0, our vector, belongs to the subspace, basically spanned by let me write it this way. Let me call this matrix G, okay, by the span of columns of G, okay? So basically, these three vectors, remember I was drawing to you this stuff, right? So trying to imagine it. So you have in a high dimensional space, you have this triplet of topographies, G corresponding to X coordinate, to X orientation of a dipole, Y and Z, and then you have your data, and you are basically trying to see how much your data belong to this subspace. In 3 dimensions, it's very hard to draw, right? Because any vector in 3 dimensions can be described by 3 orthogonal vectors, by a linear combination of 3 orthogonal vectors. But if you imagine the situation that we have let's say, I already drew this way, but I just remind you, a 2-dimensional thing, okay, a 2-dimensional space, okay, and then you have your this will be gx, for instance, and this will be gy, okay? And then you have your data, and all you were interested in find, and there are many such gx, they depend on r, right, on location r, okay? And all you are measuring, you are basically measuring the amount this guy projects into the subspace, where this plane now is a subspace, right, of the three-dimensional space that I attempted to draw, right? Uh, the amount, yeah, the amount of the amount, the extent to which this guy projects into the space, okay? And how do you measure it? You are measuring it basically by looking at how big this guy with respect to this guy is, right? Right? If this guy in projection is exactly equal to this guy, then basically,
Sorry.
yeah,
Can you choose another pointer? This because
yeah.
when you are saying this.
This way. Okay,
Okay.
So if this original data vector, okay, you think it's that simple? It's not that simple. Okay. Anyway, if this original data vector, right, which is your x, right? Let's say of t0, right? If this original data vector projects well into this plane spanned by your model vectors gx and gy, corresponding to location r, right? Because you're sampling, you're taking different locations, you're taking one location, another location, the third location, so you're scanning through the entire space, right, in the brain. Uh, uh, I thought it was a solution, but it's no, there's no solution to this problem. Anyway, so if you are, you can let me try. Yeah, maybe this way. Yeah, yeah, maybe this way. Yeah. So that's not exactly what I meant, but anyway, um, uh, yeah. Sorry. Yeah, basically, if this guy, let me if this guy projects onto this plane, right? And if it projects well, then the difference between this vector, right, and its projection, which is this difference, right? Difference, difference. This difference is gonna be small, right? So, and you were trying, if you remember, we were trying to minimize something, u transpose x of t0, right? And we were trying to minimize the norm of this guy, but in some sense there was a yeah, the norm of this vector, right? Because uh, because if this vector this norm is small, then it means that this norm is exactly the square of this guy is exactly the height of the distance, right, of this vector linking the original vector and its projected version, right, into the model space, right? And then if this guy is small, then you are happy, but this is equivalent to maximizing this guy, right? Why? Well, because U and U transpose are the orthogonal matrices, and orthogonal matrices, it means that they don't change the scale. They have unit norm, right? These matrices, the columns have unit norm, and they are orthogonal, right? And therefore, you can't, in no way you can choose such a U, and U depends on, of course, U is the SVD of your model vectors, right? So U depends on GI, but this is some sort of, you normalize them, right? Or do Gram-Schmidt orthogonalization, if you will, and normalize them, right? And that's where you get your use from. And all they can do, they can only project the vector x onto the space spanned by the columns of U, okay? And the projection can never be larger than the vector itself, right? Because if this is a vector and I project it, let's say, on this direction, that this is the direction, and according to the triangular inequality, this guy, and this is 90 degrees, this guy can never be greater than this guy, right? So therefore, it's legitimate to look for such U, and U itself depends on R, on location, such that U of R transpose X T0 is square, right? The square of this is maximized, right? So basically the norm of this vector is maximized, okay? So again, I want you to understand, because this is very important, I want you to understand that let's look at what this guy is, okay? This is just simply the notion of projection. I don't know how much you're familiar with it, but this is important, okay? So let's spend some time on this. This thing is simply, again, u is a vector, right? And u of r is u1. I will not write r here, okay? U1 and u2 in this case, or maybe u3 if you have three-dimensional model, right? But let's assume two because to save space and time. Okay, so this is u1 and u2, and you are taking the transpose of this, so it will be u1 and u2 transpose multiplied by your data vector. I used MATLAB notation, but this is just a column vector that is corresponding to the time slice of our data, right? Then clearly, we can write it u1 transpose, u2 transpose, right? Multiplied by vector x of t0, and that will be equal u1 transpose x. I will again remove since in the brackets, okay? Omit them. u2 transpose x. What are these? What are these? These are the coordinates of vector x in the coordinate system formed by vector u1 and u2, right? Because if this is u1, this is u2, and this is x, then these coordinates are u1 transpose x, and this coordinate is u2 transpose x, right? So therefore, these are the coordinates of decomposition of the elements of this vector are the coordinates of decomposition of vector x in the coordinate system formed by two vectors u1 and u2, okay? And now you're taking these coordinates, okay, and again reconstruct.
Excuse me, I have a question,
Yeah,
please.
go ahead. Yes.
And here, as you have mentioned that u1 and u2, they too are also vector, or what are they? I mean,
U2, u1 and u2 are the both vectors.
and they are
U1,
like two-dimensional vectors. Yes, x and y, they are represented.
they are usually they are of the high dimension, the number of sensors that you have. Okay,
Okay.
let's say number of sensors by one, each of them. Okay,
Mhm,
number of
okay.
sensors by one. Okay, so it's an abstract space, right? You are in this abstract space where
Mhm,
you've taken basically how you arrive to u1 and u2. You take your, or usually there are in EEGs there are three of them, u1, u2, and u3. Okay, so
mhm,
basically how you do, you take gx, gy, and gz,
mhm,
which is your topography, just corresponding to three orthogonal dipoles. Okay, so and you take SVD of this matrix. Okay, and you arrive at USV transpose, where this is a matrix, this is a matrix, this is a matrix, and U spans the same space as GX, GY, and GZ span. So it's just a basis in the space that is spanned by GX, GY, and GZ. So basically span of the column space of U is equal to the span of the column space of GX, GY, GZ matrix. Okay. All right. So and
yes, thank you.
yeah. So and then from here, right. So anyway, back to the to this. So you thank you for the question. It's very good that you're asking them. All right. So then you take then these are the coordinates, right? These are the coordinates, and this, right, this two where the question marks are. Okay, and so then you are taking these coordinates and you're again, look, so you've taken, we have this construction, right? U transpose x, right? We figured out that basically now this whole thing is equivalent to u and then a vector of coordinates, right? With respect to vector u1, let's call it this way, and u2, right? I just denoted them this way. These are just scalars This is just numbers, and U is a matrix, right? And again, because we have two of them, so you have U1, U2, right? Multiplied by C1, CU1, and CU2. These are just coordinates of this vector X in the coordinate system defined by U1 and U2, and you get U1 times coordinates, sorry, U1 plus U2 times coordinate U2. Basically, you are reconstructing this projection, right? So you're taking this projection coefficients and multiplying them by the vectors, because projection coefficients are not vectors, right? When you talk about vectors, you say, well, vector 1 is with coordinates 1, 3. Well, these are the coordinates 1, 3. The vector itself is 1 multiplied by the first basis vectors plus 3 multiplied by another basis vector. And unless you know what these basis vectors are, you actually don't know what the vector is. Okay? I mean, it's convention that, yes, it's a Euclidean coordinate system, and if this is vector 1, 3, it means that the first basis vector is 1, 0, and the other one is 0, 1. Yes, but it's just a convention. Okay, so therefore this guy, this construction U transpose X is nothing else but the vector itself. Okay, vector itself of projection of X onto the model space. Okay, and X is your time slice of the data. All right, so and you are interested in measuring the length of this vector, right? And because this guy in fact doesn't change the length, right? Because its coordinate, it's the length of it has unit length. This is unit length, and this is unit length, right? These are just basis vectors. Therefore, the length of this projection is equal CU1 squared plus CU2 squared. Agreed? Right? And so all you need to do is to take basically, it's not equality, but you have to say that you are interested in the Frobenius norm of this matrix, and the Frobenius norm of this matrix is in fact the sum of its squares, and because the orthogonal guy doesn't change the sum of the squares, then it's equivalent to just simply saying that this is the norm of this guy. Okay, U transpose X. Okay. This is the vector, right? And you are trying to maximize this, right? And again, look, you are maximizing, you have two orthogonal guys, right? You have U1 transpose X squared, right? Plus U2 transpose X squared. And you want to maximize this, right? X you can't change, right? All you can do, you can change your G such that your U will be different, right? Here on the top. And therefore, this whole thing means that you are again computing, because this one is equivalent to writing U1 transpose X divided by the length of X multiplied by the length of X, right? Plus U2 X divided by the length of X multiplied by the length of X, right? It's again equivalent to maximizing the cosines, but now you're using not a single model vector because you had single model vector, but the basis vectors that span model subspace at corresponding to location R. And you are basically looking for this cosines, for the sum of this cosines, right? For the squares of this cosines. And if the sum is big, then you are happy. Then it means that you've chosen the proper G. If the sum is small, then it's not something that you are looking for, because your data do not project, you can say it this way, your data do not project onto the model space. Okay, so it's of course a jargon, but I mean, it's means do not project. I'm saying that the projection is small. Okay, the model, the data, the time slice projection into the model space is small, and so you are scanning through it and finding. So basically, all you do is then you take your brain. Again, there are points here, and at each location in the brain, you can get this scan value, right? And then you can depict it. For instance, it will be, let me, it will be something like this. I will draw you with level lines, right? Because I can't really, I don't want to switch. We will switch and we will play with MATLAB code today as well, but just you'll get something like this. But assuming that this is the maximum, this is the highest point, right? And you do it for each point. So here, just very small, something very small, something very small. And then where this guy is maximized, then argmax of this scan of this UU transpose X squared is your location that you are looking for. Okay. So basically, see, we've started from a single dipole and single time slice, so a single topography and single time slice. Then we said, okay, we have 2 or 3 topographies, depending if we are in MEG case, we have 2, in the EG case, we have 3, because of this radial stuff, right? Remember, and then we basically arrived at the very same equation and the very same formula as we had with a single dipole, single topography, because all it is just measuring the cosines between the projection, the value of the length of the projection. Okay, and in a one-dimensional case, this projection is measured only by one coefficient. In two-dimensional case or three-dimensional case, you have 3 coefficients, right? Okay, now why on earth we are working with U and not with just GX, GY, and GZ? You may ask. Okay, why? Why don't we just say that GX, because it will be simpler, right? I mean, GX transpose X squared plus GY transpose Y squared plus GZ transpose, not, sorry, X, of course. Again, X here, right? And X here, right? And this one is squared, right? And then try to maximize it, okay? Find such G that this guy is maximized. The problem here is that it will be redundant, okay? Because nobody guarantees the orthogonality of GX, GY, and GZ. The dipoles, physical dipoles that underlie these topographies, that correspond to this, they are orthogonal. But the topographies themselves are not orthogonal, okay? And therefore, you can't do it this way, okay? You need an orthogonal system so that when you measure the projection onto this guy, this projection tells you nothing about the projection onto this guy. And these 2 projections tell you nothing about the projection on this guy. It's like in the 3-dimensional space that you're all used to, right? If I give you 2 coordinates, all you can say that this is the vector that ends somewhere on this line, right? But it can be any vector. It can be a vector belonging to this plane. It can be this vector. 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 So and then this lack of information corresponds to the fact that measuring the projections onto these 3 vectors, you're gaining unique information about orientation of this target vector in this abstract space. Okay, and once you have this information, you can add all them together. It's like, okay, it's like this. Remember when you have a it's a summation of the vectors, right? If you have 2 orthogonal vectors, right? So this is V1 and V2, for instance, right? So then the length of the sum of these 2 vectors, right, is V1 length squared plus V2 length squared square root, right? So this is the length of V1 plus V2. If V1 is orthogonal to V2, okay? But if V1 is not orthogonal to V2, if you have something like this, right, then clearly this guy, it will depend on the cosine of the angle between these, right? And the formula will look something like V1 length plus V2 length plus 2 cosines between vector V1 and V2, okay? And multiplied by V1 length, V2 length, okay? So if they are orthogonal, then this cosine is 0, and you get the original formula, right? Not the original, the simple formula from the Pythagoras theorem, right? And if they are not orthogonal, then you have to take this guy into account because they project onto each other, okay? And therefore the coordinate of some abstract another vector, right? Let's say this is 2-dimensional plane, and then let's assume let's assume that you have another vector in a 3D space, okay? The coordinate projection onto this guy and coordinate projection onto this guy, they will be mutually non-independent. They will be informative of each other because these two vectors are not orthogonal. Therefore, you need orthogonality in order to make judgment about the extent to which your hold on, where it is, to which your data vector fits into the space spanned by the columns of your forward matrix, of your forward, the three topographies for your dipole, right? Okay, is this clear?
Yes.
Okay, should be clear. All right, very good. So now we are transitioning to another slightly more I'm trying to delay the statistical stuff from you as much as possible, okay? But at some point we will have to look into it. But let's try to avoid it for now as well, right? So now let us assume that what we have is that we have a we have a slightly different story where we let me open. I have some notes, but I mean it's still trivial. But I'm just afraid to make a stupid mistake, and then I will be looking for it in front of you and wasting your time, basically. Okay. Now let's assume this. Let's assume the following thing. You have the data, and you have now, let's say, two dipoles. Okay, located and somehow oriented here, right? And dipole 1 is active with dipoles, right? Dipole 1 is active with S1, let's say something like this, okay? This is time, this is current, okay? And it has S1 of T activation, S1 of T. And the second dipole, I will draw it. Let me draw it on the same place so that not S1, S2, but I just do it with the red color, or no, with the green color. Okay, and then the other one, let's say, let it be active with this kind of profile. Okay, and this will be S2 of T. All right. So
I'm sorry.
yes,
What does notation as it's
some
signal
series.
for signal?
Yeah, signal. Yeah, signal.
Okay.
Source signal. Sometimes you
Source.
may sometimes we may denote them with J.
So it's I mean its measure is volts in.
It's not SVD. It has nothing to do with SVD.
No, I mean its measure is if it's EEG then it's volt.
No. If it's if either it's EG or MEG, it's a current dipole strength. Current dipole strength
Yes,
corresponds
yes.
to the amperes times meters, because dipole can be long but with low current, but can be small but with stronger current, and it will be the same. It will be seen identically outside. Okay.
Okay.
So
Thank you.
okay. So, and this is a very good question again. So yes, let's say that this is amperes and meters. Okay. All right. So, and then we will say that yes, then we have our data, and we simulate the data as x of t is equal. So we have sensors here, right? And we have our data multiplied by S1 of t plus G2 multiplied by S13, and maybe some noise, but we ignore for now. We will in simulations, we will do noise, but for now, ignore. So again, this is the vector. This is a vector. This is a topography vector, right? You can think of, you can always I want you to visualize it this way. So basically, you say that, I will redraw it, but anyway, you say that this is this thing, okay? Or better yet, this thing. Okay, so this is this guy, okay? This is this guy. And this one is let's say this guy. Okay, this is a topography, okay? And this guy is basically a reading of these topographies at different locations, the way they are projected, to your sensors, right? And these guys are modulating the amount with which either this projection, either this dipole, or either this topography, or the spatial pattern, however you want, or this one is present in your data, okay? If this one is small, and this one is large, then your data will dominantly look like this, right? So you can draw your data, you will be able to draw your data approximately, of course, something like this. If on the contrary, this guy is strong and this one is weak, then you will draw your data, your data will more likely look like this, okay? Okay. And again, this is, if you didn't get it, this is a nose, those are ears, this is a nose, these are ears, okay? This is a nose, those are ears, okay? So this is the head, right? The projection of the head. Okay, projection and not in the sense that we were talking about, but in some sense as well, but you know. So anyway, so this is your data, and you are not any longer, well, there are two options. You know, the first option, you always can do this. You can say, well, listen, I see this data, and if I project them on the sensors, I can draw the sensor time series, and they will most likely, no, I mean, they will look something like this. You know, so I don't know very accurately, but they will look something like this, and the other one will be like this, negative direction, something like this. But anyway, so you will have two, I'm sorry, this is not very well drawn, but anyway, so you will have two distinct peaks, this peak and this peak. And this first peak corresponds to this moment of time where one dipole is active and the other one is slightly active, not really strongly active, right? And then you may probably, especially if you see this peak which are distinct, right? You may find another location in time where this guy is dominating. I'm sorry. When this other dipole is dominating, you know, for example, you can find the point in time where this second dipole is zero, the first dipole is zero, and the second dipole has some. And the second dipole has activation, right? But the problem is that you do not know these time series, right? I mean, that you need to find them, right? You don't know how the dipoles are activated. So if looking at the data, you have some intuition. If you look at the data, you really see clearly dipolar pattern corresponding to certain time slice, then you can do what we have just described. I described to you. You can take the single time slice and do the dipole fitting, no problem. But if the sources are active together, it's very difficult to find where these sources are and isolate time slices where one source is dominating, significantly dominating the other source, right? Because again, your model, in order to fit the model, you need, like in this classical setting, in the setting that we have just discussed so far, right? You need to isolate the activity of one source from another source, right? Because you are fitting single dipole model, right? You're checking if this guy is a dipole, right? And if these two guys are active, then you will have a picture that looks rather like this, right? It will be black here, it will be black here, and it will be very strong red here, right? I mean, I don't know. It's just very ugly face, right? So anyway, you will say this is unintentional, sorry. But anyway, you will have you will have this, right? And this is not a dipolar pattern. So you will not be able to find such a G, to find such a location that that matches that matches this pattern. So you will not be able to find G such that cosine between your X, which is this, and your model at any R is large enough, right? So, and therefore you need some other methods, okay? And there is such method, it exists, and it's very practical. It's a slightly different approach, okay? It's called, but the way we are discussing it, I will try to not make a very large distinction between the way we discussed this whole thing so far and how this method is introduced, because you know, to do it like academically, I would need to go into describing to you what the covariance matrix of the data is, and other stuff. You know, it's very difficult for now and will confuse you a lot. Okay,
We
so
discussed a bit during seminars. this
we
thing.
will discuss it today anyway, because we will, if we have time, we will go into beamformers, and this is where we can't do anything without statistics, right? So we can't do,
Mhm.
but I mean, you don't, but at the same time, it will give you understanding that the covariance matrix is basically, you use here the covariance matrix in order just to measure the signal subspace, okay? And you can extract signal subspace if you're dealing with average data, okay? If you're working with ERP data, then you technically don't even need covariance matrix, okay? Because it's really not a covariance matrix, okay? Because it doesn't capture a lot of statistics in it, because the evoked responses are short and averaged out, and everything is kind of, yeah. So anyway, you don't need it for now. Anyway, so how we proceed? Okay, let's do exactly the same way, except for one thing. Okay, so we were here. Let me go back and show you here, right? We were maximizing here. We were maximizing this Frobenius norm of this guy, which is just the sum of squares of the elements of this matrix. Okay, so basically, if you take matrix, and the sum of squares here, the sum of squares here, sum of squares here is equal to the sum of squares here, and the sum of squares here is simply the sum of coordinates, the sum of squares of the coordinates, in other words, the length of your projection. This is solid, right? This is, you understand this, right? Okay, now, again, from the same very setting, assume that now you have the data and you have, you look at some interval in time, okay? So, and this matrix, because this will be a matrix, right? So here is this interval in time in your data. And if this guy is x of t, and this is t, right? Then denote this as a matrix x, okay? Which simply corresponds to x t0, t1, for instance, at the matrix, and this is t0, and this is t1, right? Okay, so and assume that you have this matrix, and now you assume that you also have some unknown sources, right? And now you have also vector of sources, and when this vector of sources is s1 of t and s2 of t, right? Now assume that you also sample this activity of these sources in the same time range, and create matrix S, which will be S1 of T0, S1 of T2, and etc. Wait, no, sorry, I mean, I don't. This is not the right way. So basically, assume that you will have here S1 of T0 to T1, okay, and this is S2 of T0 and T1. Okay, T0 and T1 are, this is just the two numbers, meaning that you have to take samples of S is in this time range. Okay, so and that's your matrix. Okay, this is your source matrix, and then you can write the difference between the observed data matrix X, this guy. Okay, oh, very nice. Okay, between this matrix X and your some unknown G, okay, which you don't know, but it doesn't matter. It never frightened us, right? And we want this, and Frobenius norm of this minimized. So basically, we take the data, the original data, the measured data. So let's call them measured data. Measured data. And this data we will call synthetic data. It shouldn't frighten you because remember, in the very beginning we also didn't know G, remember, and we didn't know A, right? Remember, we had this G and A, and that was a scalar, that was a vector. Now, since I'm a little bit more complicated, this is a matrix and this is a matrix, but it's nothing to be afraid of.
I'm sorry, can you
Yes.
repeat one more time? What matrix is G?
G.
Yes, G.
G is your known forward model matrix corresponding to the in this case to the two dipoles, okay? So you
So
don't
it's
know.
some
So
noise.
no, it's
It's
not
some
noise.
it's not
G
noise.
is G. Let me show you. It's a good question. Hold on. Gx of R, no, not Gx, G theta, okay? G theta of R and G theta of R1, okay? And G theta of R2, okay? Let me explain you. Yeah, good question. Although you don't know it, but you need to at least know how approximately something we are looking for looks, right? So G is, remember when we had in the very beginning of we had this setting where we had forward model G, which we didn't know. We had this measurement A, and we had our data, remember, and we were trying to minimize this. And then we solved this, we expressed A from X using G, we substituted this expression for A, and we arrived to the fact that we need to minimize the cosine between G and X. Maximize, right? So it's essentially the same thing, but just scaled to the case where we have arbitrary orientation. But arbitrary orientation is a little bit. Let me tell you. Let me show you. Let me tell you. Yeah. Forget about now arbitrary orientation. We will arrive to it. But these G matrix G, in this case we are looking for, has only two columns because we have two sources, and its columns are the topographies of the sources that are already oriented. Okay, that we don't know their orientations. We will find them, but they are somehow oriented and fixed, right? But unknown. And then if we multiply this matrix by the activity of our sensors, right, of sources, sorry, S1 and S2 of T, right, I will get my data. Okay, so this guy scales this guy, this guy scales this guy scales this guy. Okay, and you get your data, but you don't know any of them. Okay, all you know is your data, this, and you know Maxwell equations, and you can compute these columns, these guys, for every location R. Okay. All right. But again,
Okay,
this
thank
is a
you.
very similar setting. I mean, just don't be afraid. We just expanded it. We said that we have two sources simultaneously. Okay. Before we were saying that we have one source, but it had two topographies, right? Here we also imply that there are two topographies, but it's hidden. Okay, two topographies per source, three topographies per source, but it's hidden. You will see. Don't bother with this for now. Okay. So.
Okay. And I
S-
have a little small question.
yeah,
For will we have different access for these two access?
different what? Different what?
Different access, different models for two sources.
I'm sorry, I missed the last two. Maybe you'll say in Russian. Sorry, different what?
У нас для разных, вот у нас есть два источника, у нас для них будут разные иксы сейчас?
No. Okay, no. We are measuring things simultaneously. See, they are active simultaneously. So there are two sources, and they are active. This is one source is active, and this is another source is active. Okay. And
Yes,
and we measure, the whole point here is that we measure the superposition. Okay, we measure the sum, and we don't because yes, if you could say that, if you could tell the brain, listen, activate the source in the temporal lobe, okay, and brains activate the source. You say, okay, I know where it's located. Basically, we do it this way. I mean, we do it this way when we want to localize sensory cortex, for instance, right, of corresponding to a finger. What we do, we apply electrical stimulation to the finger, right, and we know that the very early activation arises in the sensory cortex corresponding to the where the fingertip is represented. Okay. And we assume that this is a single source, and yes, the dipole modeling is very simple. But if you apply this dipole modeling to analysis of evoked response data, for instance, right, or which may be very complicated, several sources active simultaneously, or even if you just look at the auditory data, when you send some auditory stimuli to both ears, you will have activations, simultaneous activations on both sides of the head, and you need to somehow decouple them. Of course, in this simple case, you can just take one half of the head and the other half of the head, right?
Yes.
But if you take, like, say, if you analyze interictal spikes, for instance, right? You have a
Mhm.
spike, and it may have two foci, two epileptogenic foci, or two irritative zones which are close to each other,
Mhm.
and you need to disentangle them. You need to find where the first one, where the second one, but they're together and you don't know where they are. Okay.
Mhm.
So the whole
Mhm.
point that you're observing the linear combination, as we say, a linear, this thing is called, I mean, I'm sorry, it's drawn on the top, but this X is a linear combination of G1 and G2 with unknown coefficients S1 and
Mhm.
S2, and G1 and G2 also not known. So,
Yes. Okay.
okay.
Thank you.
So it's in a way hopeless problem, but as you will see, not. Okay. So anyway, so yes, and then let us go back to this equation, to this expression. Okay, to simply the Frobenius norm between the actual data and the some synthetic data. Okay, so I will again try to draw, although I'm doing it horribly. Well, I can draw actually, but I'm somehow, when I'm giving a lecture, I'm very nervous, and therefore I'm always afraid of like spending your time and blah blah blah, and things like this. So therefore, I yeah. Anyway, so anyway, this is your assume that this is your data, okay? This is your measurements, okay? And this is your X, and then you want to recreate such G and S so that your GS will look, let's say, something like this. This is like on this and for this channel, for this channel, for this channel. So they will look kind of your measurements, but not exactly. And then and this is your G times S, okay? It's again a matrix, right, of the same size as X, right? And then if you compute Z, which is equal X minus GS, right? Then Z, the red one, okay? Then it will be something like this, right? Some noise, right? Not noise, some remainders, right? Some inaccuracies of your model. Okay. And this is the sum of the squares of these guys, of the red guys, you want to minimize. Okay. Okay. The sum of squares you want to minimize. Okay. That's what X minus GS squares minimize means. Okay. All right. So, and let's proceed in exactly the same manner. Well, we can take the derivatives, but let's not do it. Let's do this fast lane thing. Let's rewrite this guy. And let's say if this one is 0, right, then this is equivalent to saying that um, this one is equal to this, right? Then you can say that, okay, then you can multiply by G transpose both sides. Okay. Again, you don't know G transpose, but come on.
Uh,
Don't you? Yes.
ah, okay. It's
Yeah.
just
Yeah.
G transpose. Okay.
Yeah. And then you pray and make sure that this is invertible. Okay. If it's not invertible, there are always tricks, but we just ignore them for now. And then you multiply by both sides on the left by the inverse of this guy, G transpose G inverse. Okay. Of course, G transpose G in this case will not be invertible, but you know, just ignore it for now. And then multiplied. No, G transpose G will be invertible in this case because we have only two dipoles. Yeah, no problem. Yeah. So G is equal, if you multiply it by inverse on the left, this guy, it will be identity here. So it will be S, right? And this is exactly the same as we had before, except that, remember, instead of S we had A, instead of G we had G is this, just vector G transpose. Remember, it was exactly the same in the very beginning of the course, right? So very similar. Now you take this guy, and you substitute it here, okay? And then, and let me see if I didn't go, because I'm so much afraid of goofing and making mistakes. Yeah, of course I goofed because it has to be X here, right? And you didn't tell me. So, and then you will get this X minus G, okay, this G matrix multiplied by G transpose G minus first G transpose X, right? Again, and you want to minimize this, okay? Okay, now, by the way, do we need to have a break? What time is it? I don't have
We
what.
have 4 more minutes.
Okay, good. So now, again, this is instead of minimizing this as before, we will be maximizing this, right? So we will write G transpose G minus first G transpose X, and all these are the matrices now. But nothing changes here. Matrices, but nothing really conceptually is changing. And you want to maximize this guy. And now the same trick. And let me just not write the whole thing. Okay, all you do, you say that G is UG SG VG transpose. Okay, you just represent your matrix using singular value decomposition. Are you comfortable with this, by the way?
You mean do we understand it?
Yes. Do you understand
Yes.
more? Okay, cool. So
I
you
mean, it's like easy and hard at the same time. It's kind of mixed emotion, mixed something.
yeah, it's good. Mixed emotions are good because you know when they are, I forgot the word in English. If they're flat, but what is the word for the preternae? What is the word in English? Flat is one way, but no, but not, but there's a better word.
One-sided.
Yeah, I can open your flat. Oh yeah, preternae. Preternae. What's the word, by the way? Must be beautiful word for this. I. I.
Cloying, sugary.
No, not that. No, that's not the word. That sugar is, you know, it's play, you know, it's preternae, not in the sense that it's well, maybe
Cloying.
flat, plain, exactly, plain. Yes, plain emotions are bad, right? Plain emotions are bad. Yeah, plain, of course. Yeah. Sorry. Yeah, and then yeah, you have G represented by this guy, and remember that G is your, you know, forward matrix. G represented with this. And then you take X, because it's a matrix now, right? And you represent X as also using the SVD, okay? You can always do this, right? You can always find an SVD for any matrix, okay? It doesn't have to be squared, doesn't have to be orthogonal, doesn't have to be symmetric, if it's square, of course. Any matrix you can find an SVD of, okay? So, and then you simply substitute this here, okay? Please exempt me from this, okay? I will not do it now, right? But I will just write you the result, okay? G transpose G minus first G transpose X is equal to UG, I will copy it, okay? UG transpose UX SX VX transpose, okay? So this horrible thing reduces to this guy. One thing to note here, it's actually very interesting. Well, first of all, we are interested, of course, in the Frobenius norm of this guy, in the sum of squares, right, with elements. But one thing to note, see, we have, if you just think about scales, okay, the scale units, think about units. Whatever units G has, the units will be canceled, right? Because you have G squared, essentially, divided by G squared, right? So this is G squared divided by G squared because minus first here. And this one multiplied. So if G is measured in, I don't know, in ohms, for instance, then it will be ohm squared divided by ohm squared, okay? Right? So therefore, there is no scale to this matrix. So it's only shape, okay? And therefore, if you look at the result, it's basically UG transpose. That's it. That's it. What's left from this guy, okay? And UG is a orthogonal matrix that has unit norm vectors, okay? The columns, unit norm columns, okay? And of course, as a scale, because you didn't divide it by anything, it's just an expansion of X with this thing. Okay, now 2 more minutes and you'll go for a break, okay, to digest all this. And then if you're interested in a Frobenius norm, then the multiplication by the orthogonal matrix doesn't change it. Remember, because it's basically the sum of squares of the coefficients, because you can consider everything you can consider as a vector of or columns like of a matrix multiplied by vector by another matrix. You can consider the coordinates of this column in the space spanned by the columns of, let's say, UG, and then it will be just essentially sum of squares, right? And you can ignore UG because the vectors are normalized, the columns of UG are normalized. The same thing about Vx, because Vx are orthogonal vectors, a set of orthogonal vectors of unit lengths. Therefore, this guy can be rewritten in UG, yeah, I forgot. Sorry. UG transpose UX SX, okay, squared, okay, and you want to minimize this, right? So now, if you assume if you just ignore, I have it like another set of, but anyway, there are different approaches here, okay? You can't, the way we were doing it so far, we were not taking into account the amplitude of X of your data, right? Because amplitude is stored here, because this one is unit norm. This is a diagonal matrix where we have all powers, right? This tells us about the size. I mean, the size of our X, right? Not the size in terms of number of rows, number of columns, but about the magnitude, right? About the amplitude, right? So if we ignore this, we will be just looking for the shapes, and it is essentially the same thing as before, except that now we have UG transpose before, whatever, but then UX, the first guy from UX, and this Frobenius norm of this, right? And UG transpose UX, the second guy from this, and again squared, and again squared, right? So it will be just you are projecting your UX onto those two vectors, for instance, or n vectors, whatever, of your model space, and looking at the coordinates of them and summing them, and then you take another vector that come from your data, right? It comes from your data, and projecting it and summing all these squares. Okay, the only thing that you have added, you have just added another set of coordinates, basically, that you need to add to the metrics of the quality of fit, of the goodness of fit. Okay, so again, before, when we had a single topography and the single time series, but not even single time series, single value of activation of a single source, right? Not a vector, of course. Right? We had it. We had the simple thing, which was G transpose normalized multiplied by your data, and you wanted to maximize this, right? Then we added arbitrary orientation. We had now two guys to sum, right? Two guys to sum, because we still had the same time slice, only single time slice. And then you added arbitrary shape of your data, and your arbitrary shape of your data may have several columns in UX which correspond to the activity in time. We describe the spatial diversity of your data. We will speak about it next hour. And then you add in another set of squares and this is your quality metrics, and you're trying to maximize it. You're trying to find that, and how to do it in details I'll show you next hour.